Okay, so we're in chapter 12 now, Survey to Organic Chemistry. And the reason it says survey is because it's not, a full-out organic course. And I was telling my first period that, yes, this is Southern Regional Technical College. And if you transfer up to, say, I know some people want to go to huge, the bigger schools like Tech or something like that, you'll end up taking their versions because they have they're very specific. They're not, the elite in the nation for no reason at all. But even if you do, having this is going to be a great stepping stone for you. Number one, you're going to appreciate having a background before you go into the brick wall. Then another thing is this: even if you want to go and be whatever in your life, in college you're going to end up having to work part-time anyway. If you, by the time you leave this high school, one more year to technical college would probably get you your LPN, your RN, whatever, because you're going to have at least 2 full years, some of you maybe even 3, depending on whenever you start taking this stuff. If you do that before you transfer up to a bigger college, you can get a part-time job working for like real pay and benefits. And that's a huge thing, because if you're going to work 20 hours a week, it would be nice to get paid, if you're like say an LPN or an RN, $15, $20 an hour, as opposed to working at a fast food restaurant for $8 an hour. Okay, so that's a really good option for you to do. So take advantage of this and really think about, while you're applying for colleges, if that's something that you might like to do. Yes?
Can I turn this? This is like cold.
Yeah. Okay, so also from here on out, I suggest that you bring your textbook with you and turn with me as we're looking at stuff, because when I'm drawing stuff, Hunter, did you turn in your lab?
I have no idea.
Okay. Yeah, put it right here in this black bucket. So the reason is because, I draw something a certain way, but it's not going to be exactly as it is in the book, and you need to be able to see both ways. All right? But organic chemistry deals with carbon chemistry. And this is going to really help you. It's going to be a real eye-opener, because this is so real life. I remember when I was getting my BS in chemistry, I was taking a couple years worth of inorganic classes, and I thought, I still cannot even read a label on the bottle that I'm drinking. And the reason for that is that almost everything we do uses carbon chemistry or organic chemistry. There's different naming systems and so on. So once you learn this, it's going to open up a whole new world to you. Another thing is our system and our society has completely bastardized the word organic. Now, linguists will not call that a bastardization. They'll call it a natural evolution of language. But we have turned that word organic into meaning some kind of food that's never going to harm you or something. Okay, organic farming, organic whatever. The word organic means dealing with carbon. Even plastic is organic. Okay, plastic is man-made, but it is still organic. And so you can see where somebody who's studying chemistry has a big negative reaction to labeling things organic, because plastic is organic, but it is not good for you to eat. eating something like, some poisonous substance that comes out of the ground. You can eat poison ivy. Well, that's organic, but it's not good for you. So we have, a lot of times you'll see us kind of cringe at the use of that word. But it has a different nomenclature system. And I'm going to use an S on that word because we're learning, just like we did with inorganic chemistry, that you have common names and you have the IUPAC names. Remember, the International Union of Pure and Applied Chemistry? So again, we're learning multiple names for things. And we're also going to find that we have multiple ways of writing formulas and drawing things, which puts another little kink in our hose that we have to deal with. But since it deals with carbon chemistry, it has covalent bonds, so they're going to have characteristics of covalent bonds that you need to remember. Now, I do not have time to go back and rewrite all these out for you or reteach all these. But if you look in your textbook and you're having trouble remembering something, your textbook has these little arrows here. You see those little arrows right there? And it'll tell you if you're having trouble with this, go to such and such page and re-look it up. Do what now? Whatever y'all need. Good with me. Okay. Alright, so since they have covalent bonds, you need to remember the properties of those covalent bonds. And you also have to remember that carbon has 4 bonds that it can form. So 4 bonding sites. So we call it tetravalent. If you'll remember from covalent nomenclature, tetra means what? 4. So we have 4 bonding sites. So remember also, and REM is just meaning remember, that they're going to be insoluble in water generally. They're generally not going to conduct electricity, and that covalent bonds may have partial polarity. We're going to see this delta positive sign again, and we're going to see our delta negative sign again. Remember last semester I think I went 2 or 3 weeks using sigma instead of delta because my head just needed something to be hit, I guess. So let's make sure we have that I haven't damaged you psychologically by using that wrong Greek letter term. But remember, this is like a capital delta, and that means change whenever we're dealing with anything in science. This is your small delta, and we use it to deal with partial polarity. In addition to that, in organic chemistry, we need to, well, also in inorganic, but we need to understand the direction of our positive charge versus our negative charge. And so we're going to do that. A lot of times we'll see this symbol. This signifies where the partial end is and the partial negative end is and where the partial positive end is. Okay, so this is our partial negative, and then this looks like a plus sign here. This is our partial positive. So we're going to see this more often. And another thing that makes organic chemistry, there are a few things that make organic chemistry kind of difficult. So we've already mentioned one, is we've got all kinds of different naming structures, naming rules to deal with. We've got different ways to write structures. That's kind of difficult for people to deal with. And here's the other thing. Females, and again, this is a stereotype. This is something, just because you're female, that doesn't mean you necessarily wear this hat or fit into this category. But females tend to be not as intelligent spatially as males do, meaning that gives us trouble rotating things, turning things around. Females may not feel as comfortable in geometry as males, and this is one of the things that, you know, kind of causes females not to go into engineering quite as much, or some of your real technical fields where you have to have that spatial intelligence. Okay, just because we did not spring forth from the womb doing this naturally doesn't mean you can't get good at it. All right? It just means that you have to, if you don't have this natural gift, then you have to work a little harder to be good at it. So keep that in mind if you struggle. And then again, just because you're born with that Y chromosome doesn't necessarily make you good at it. There's plenty of men out there who can't give directions or who get lost easily when they drive cars. Okay, so we have to come up with some ways with dealing with three-dimensional shapes. Because organic molecules have very, very special and particular three-dimensional shapes. Remember again that shape is everything. That's why drugs can target specific things. Hormones go to specific places. Get into your catalysts and your enzymes that are shape specific. Now, we always get into that problem of taking a three-dimensional shape and drawing it on a two-dimensional surface. So in here, we're going to be relying a lot on models as well as drawings. So some things that you'll want to get used to: if an atom is pointing away from you or into the paper, you'll use dots or dashes. If it is pointing toward you or out of the paper, you'll use this kind of, not quite an arrow, fat triangle. So here's an example of what I mean. If you'll remember, carbon with that, remember it's got that tetrahedral shape, and if you take your hands and you do like this with your hands, can y'all see how I'm doing that with my hands? Do that with your hands. If you lay them on a piece of paper like this, okay, you lay them on a piece of paper, you can kind of get an idea of what a tetrahedron is. You've got your 3 points that touch the surface, and then you've got this one that sits on top. It's not perfect, but it helps a little bit. Okay, so notice that when you do this, there's going to be one that can be seen as being towards you. There can be one as being seen as like being, you know, on this side. One that can be seen as being up, and there's going to always be one that's kind of seen as away from you. All right? Do that same thing with your other hand, and you're going to notice that when things link together, and you'll remember this whenever we did a few little things with models last semester, that they don't lie flat. If there's single bonds, they're not going to lie flat on that paper. And so you're going to see that we draw things in a certain way to show that they don't lie flat if there are single bonds involved. So one example, and this is our simplest example, methane. Which is CH4. In this particular case, remember the empirical formula is going to be the same thing as the molecular formula. Remember, an empirical formula is the lowest ratio of all of your elements. Your molecular formula maybe instead of CH4, maybe it could be C2H8 or C3H12. Do y'all remember that? The difference between an empirical and a molecular formula? Okay, in this case, the CH4s are also our molecular formula. We're also going to see this thing called a structural formula. Which you've not really seen yet. And in this case, our structural formula, since this is such a simple molecule, is also going to be CH4. To give you, then we also have our diagram. We have a few different ways of diagramming things. But to give you an example where they may not always be the same, an empirical formula, remember, could be C2H8, or excuse me, that could be a molecular formula, C2H8. Remember, that breaks down to CH4 as an empirical formula. Do y'all remember that from last semester? This is where you nod or something? No? Okay, remember, an empirical formula is the absolute lowest ratio, CH4. A molecular formula could be C2H8, C3H12. It tells you exactly how many are in there. We also see a structural formula. In structural formulas, I'm going to be showing you a little bit later, but here's an example of a structural of a structural formula. CH, and this does not have the same empirical formula, okay? But I'm just giving you an example. But a structural formula might be CH3, CH2, CH2, CH3. That's a structural formula, and there are reasons why we might write it like that. But just letting you know, that is called a structural formula. And again, the empirical formula, or excuse me, the molecular formula for this would be C1, 2, 3, 4, C4, H6, 8, 10. Right? This would be our molecular formula. Our empirical formula, both of them could be divided by 2. That would be, yeah. Okay, so do y'all remember those from last semester?
Yes, ma'am.
Okay, so now we're picking up not only having an empirical formula, but having a molecular formula, and now we're picking up this structural formula. And again, there are advantages to having that, which you'll see later. You don't see them right now, but you will later. Now, we also have to do some diagramming. So if I'm looking at, going back to the example of CH4, now some of you are going to automatically ask, do you have to put your straight lines, and remember straight lines represent single bonds, or do you have to put your straight lines in that direction? No, because remember, all these things turn. They flip and they flop, so where you put them is going to depend on how it's oriented.
I thought they couldn't be straight across from each other.
Well, oh, you're right, they can't be straight across from each other, but
Don't have to be like the farthest degree possible.
yeah.
Without being in a straight line.
Yes, they do. But what I'm getting ready to show you is integrating these three-dimensional aspects. Like, so if I want to show that carbon connected to a hydrogen, and this particular hydrogen is close to me, coming out of the paper, I would use that. But the hydrogen that is away from me or inside the paper, I would use dots. And that is going to be one way.
I don't get what you're saying when it's away from you and when
Oh, so it's like a tetrahedron.
Yeah, do this. Okay, now do you see that you've got your thumb pointing at you? Okay, that's,
Oh, are you talking about when we draw the diagram?
yeah,
Oh, okay.
this is outside of the paper. This one is kind of, in this case, it's, you know, almost opposite. Over here, this is inside the paper or away from you,
So
and then this would be the,
like when you're drawing your diagram.
yeah.
Okay.
Because this is going to be very, very important, and we're not going into this just yet, but just this is going to give you a reason why it's important. Take your hands and do this. Okay. Notice that our if we were to put a formula to this, our empirical formula would be, you know, F for fingers, F4 thumb 1, T1, F4 T1. Both of them have the same empirical formula, F4 T1. But are they the same? Put them on top of each other just like this. Are they the same? No, the fact that our thumb cannot be placed on top of the other thumb like this makes it 100% different. So if you're a physician and you have a right hand, can it be put on the left arm? No, it can't be. All right? So position, placement, what's going in, what's going out, all of a sudden becomes very important, and we have to, not only when we're using those three-dimensional models, but also when we're putting on paper, we've got to communicate that. So this is where you you go, oh my goodness, this is, you kind of get a little bit mind blown sometimes.
Alright, that was just like wondering if it was something like a real paper or when you're doing a diagram. I don't know. But I get it.
Well, we're gonna do diagrams. We're gonna do writing, and we're gonna make models. Okay?
When it's colored in, it's still a single bond.
Yeah.
So if you do more than a single, you still have to color in more than a little triangle.
They can get pretty complicated. Like this is just one carbon, but say we're dealing with like glucose, which has 6 carbons, and we've got things up, down, all these different sides. And it makes a difference, because if you remember when you took biology, you had glucose, you had sucrose, you had the milk sugar as lactose. A lot of those are simply because where an alcohol functional group is, whether it's on top or bottom. Okay, a lot of things simply are different because of the position of something. So again, we're just looking at something simple, but the reason we're looking at simple now is because you got to understand what all these little nuances mean. And we learn, try to learn on the simple instead of on the difficult. But they have very, very, very important shapes. Now, remember too that whenever you're dealing with single bonds, they do not lie flat. And maybe it's lay flat, maybe that's the correct English to use. I don't know, that's why I don't teach English. But they do not lay flat. If you remember, we had all those molecules up here last semester, and they all were kind of up and down. And so you're going to see that we're going to draw them very often in this way. So get used to that. When you see a line, that line segment, this represents your actual bond, and then at the end of each line segment is a carbon. A carbon is represented. So in this case, we've got 1, 2, 3, 4, 5 carbons represented. Okay, 1, 2, 3, 4, 5 carbons represented. All right. Now, remember that your covalent bonds, so covalent bonds to include carbon can form double bonds. And not just carbon, but your other nonmetals. Where they're sharing 4 electrons, and triple bonds where they're sharing 6 electrons. Now remember, these are linear in shape, and when we bring out these models, you'll remember that whenever you have these either these 2 or these 3 fingers together. Okay, so if you got your 2 or your 3 fingers together, you've got a linear shape. You kind of don't have a choice but to make a line right there. Okay, so those have a linear shape. Remember, you're going to see a lot of hydrogens that tend to have one bond. Well, that will have one bond, +1 or -1. You're going to see a lot of nitrogens that tend to form 3 bonds. Remember, they can be a +3, -3. They can also be a +5 too. You've got your phosphorus tend to form 3 bonds, +3, -3, +5, and then they can also do some other things. That's just, common things that you see. Your oxygens almost always are going to form your 2 bonds, and just about always have a -2 charge. You've got your sulfurs. Mostly, you're going to see them as, you're going to see them as a lot of different ways, but you got 2 bonds. They can be a -2, but they can also be a +4, a +6. They can have multiple things. So, remember, go back and reacquaint yourself with those properties of covalent molecules, because you're going to need to know them. And just like we had families on the periodic table with inorganic chemistry that shared certain properties, the families of covalent molecules are known as functional groups. Now, these functional groups are going to have similar properties. If you look at your table now, in my book it was 361. I'm not sure what it is in your book, but it's table 12.1, some important families. You're going to have a quiz over that on Thursday.
This is 361.
361 for y'all? Okay, Thursday. So do not wait till then. You're going to need to pull out all your stops for this. I would invest in a lot of index cards, because these functional groups, you're going to find that is how we name things. And not only is that how we name things, but that's going to be a determinant in how they react in certain reactions. So, in inorganic chemistry, we had combustion, double replacement, single replacement, synthesis, decomposition, redox, neutralization. So not only are we going to have those with inorganic, but we're going to have them with organic, and predicting what they're going to do is all about the functional group. So you can't go anywhere until you learn functional groups. All right. Now, you're also going to see the term, and we saw this term whenever y'all took biology, and that is the term hydrocarbons. This means that they contain carbon and hydrogen. And technically, they're supposed to contain only carbon and hydrogen, but sometimes you'll see them you'll see a lot of things referred to as hydrocarbons that might contain some other things. Technically, they contain only carbon and hydrogen. But again, sometimes people will get sloppy and they'll talk about hydrocarbons a little bit incorrectly. But to be specific, hydrocarbons contain carbon and hydrogen. But I know in biology, lipids might have been referred to as hydrocarbons. All right, we're going to start out with the simplest ones. Remember, your book has it in table form, and it's a little bit difficult for me to stick to that table form here. Now, the simplest ones are called alkanes. Your alkanes, and notice the ANE. the alkanes contain only carbons and hydrogens and only single bonds. So I gave you an example of the very simplest one, CH4, methane. Notice that all of these are going to end in that suffix -ane. Now your book doesn't start you out with the very simplest one, and the reason is because they want to give you a good structural formula, and they want to give you a good line structure to look at. And with this, we only have one carbon, so it's hard to do a structural formula on it because this is the same structural formula. It's the same empirical formula. It's the same molecular formula, and you can't really have a line formula for it. So your book is going to start you with propane. All right? Propane has a single bond between your carbons. There's 3 of them. A lot of times you'll just see lines and hydrogens aren't exactly written out. So if we look at propane, our empirical formula we look at our molecular formula. The molecular formula is going to be C3, right, 1, 2, 3, 4, well, wait a minute, 1, 2, 3, 4, 5, 6, 7, 8. Does that make sense?
Well, when you count the bonds and the carbon.
Yeah, because they're bonded to carbon. Okay, so C3H, 1, 2, 3, 4, 5, 6, 7, 8. Now that would also be our empirical formula in this case, wouldn't it? Because you can't reduce it down anymore. So C3H8, an empirical formula. Here's what we would call a structural formula. And notice I'm going a little bit deeper than this chart does. I'm taking you back to first semester a little bit because, you know, they're assuming that you remember this, but I just want to remind you. All right, a structural formula. Notice that it has on this end H3C, and they actually did not draw the line with that. Let me just kind of erase my little line there. Notice that on their structural formula, sometimes what they're going to do, not all the time, but sometimes you're going to see that on their structural formula, they're going to put, if it's on this side, their hydrogen's over here. Sometimes you might see that. And that's just because somebody's wanting to communicate that the hydrogens are on this side. Okay, you might see it just like this, like what you would expect. But I just wanted to point out to you that sometimes they're going to put the H3C over here because they're just showing you that, hey, I've got these 3 hydrogens over here. Okay?
What is that dot?
that's because I accidentally was drawing a line, and I was just wanted to erase my line, and now I can't find my whiteout. So, all right. Now, another thing that they're going to do is they're going to draw a line diagram or a line structure. And some of you look like you're already kind of starting to get zoned out or off task, but you don't want to miss out on your basics, or you're going to have a harder time. Notice with the line structures, if you look in your book, they show that as your line structure. Notice that they're not going to show you the hydrogens in a line structure because it's expected that you know that. And notice they don't take time to put like dots on there. But if you'll remember, one carbon is here, one carbon is here, and one carbon is here. Okay? And again, the name of this particular one is propane. It has the ane suffix because it has just the single bonds. I've got to do two more with you, so don't zone out on me. Focus. The next type is called the alkenes. Notice that these have the ene structure. The alkenes have a double bond. And remember, carbons have to have 4 bonds or share 8 electrons. So we got 1, 2, 3, 4. And we got 1, 2, 3, 4. So an alkene is going to have the ene suffix. And if we look at a structural formula, a simple structural formula, here's where they're going to show you an example of having like H2C CH2. Notice that on this side your book put the 2 hydrogens over here. Okay, so that's a real simple structural formula. If we were to write a molecular formula for that, going back to last semester, that would be C2H4. Your empirical formula for that would be what? CH2. Okay. Now, they also have a line structure there in your book. I'm down to under 5 minutes, so I'm going to do this real quick, and then I got to get through that next one. But your line structure is, again, not going to show your carbons. But the one in your book looks something like this. I mean, their lines might be connected here. But every line segment ends in a carbon, so we got carbon, carbon.
Is this still for the alkenes?
Yeah. And this is still for ethylene. Okay? Now your book shows it all in a chart form. I'm just kind of spreading it out a little bit. All right. Then if you have a triple bond, it is called an alkyne with an Y-N-E on the end. Alkyne. All right. It looks like this. Again, that's a linear shape, triple bond. Now, here's where we're already going to put a little kink in your hose between a common name and an IUPAC name or an organic nomenclature name. But they give you a very simple one with only 2 carbons here that is called ethylene. That is your IUPAC name, but we remember it as acetylene. Okay, this is the common name, and this is a very popular thing like acetylene torches in welding. There's some interesting things about acetylene that we could show and kind of go on and on with. But notice here we got a little kink in our hose because this is the proper name, but yet throughout history, before proper names were invented, we called it acetylene. But it is really a triple bond. And so if we were to draw a line structure, it would be this. Okay, give me one more second and then I'm going to get you out of here. But again, a molecular formula would be C2H2. That would be a molecular formula. CH would be an empirical. Okay, so you see different ways that we've got of doing these things. Quiz over this table. I'm going to go over some stuff tomorrow, but remember, quiz Thursday on this, so y'all can't wait. Have a wonderful day.